So natural convection is basically just like forced convection, except that, so in convection, what was the deal? The deal was the first layer of air or fluid or crude oil, the next layer is conducting with the metal, with the solid, right? But we, in order to improve that conduction, we always would like to disturb this boundary layer. We always would like to bring fresh air or fresh liquid next to the wall so that it can increase the conduction. So convection basically works by moving the fluid by a fan or a pump or whatever the mechanism, that you always change the layer next to the wall. Maybe at the end. It's very easy. So the idea was convection basically increased the heat transfer by always changing this boundary layer. And so the V was really what's doing the trick, or the Reynolds number, because that was moving the fluid. So now in natural convection, yes, also the movement of the fluid will improve the heat transfer. You are changing the fluid, but there is no fan, there is no pump. The reason why those guys are moving is just because they got lighter, and that's why they go up. If you are heating them, like this egg trying to get cooled, or if this soda can, it's really, really cold, it will make the air next to it very cold, and it will get heavier, and it will drop. So that change in density, because of the temperature is what generates the movement, what improves the heat transfer, because he's refreshing the boundary layer. He's bringing new fluid next to the wall. So we are going to use exactly the same equation. We are going to use Q equal HA delta T, right? HA delta T, where delta T difference between the fluid and the surface he's trying to heat or cool. And that H will come from a Nusselt number, of course. H will come as function of Nusselt number. But that Nusselt number, this time, remember last time we had Nusselt number function of Reynolds, because that's what's moving the fluid. But here, there is no Reynolds number. He's not moving the fluid. It's not the V. It will be some other dimensionless number that will result in this movement. And that dimensionless number is basically related to the buoyancy. The fact that you get hot, you get lighter, you move up. Right? So expect a new number. That number will be called the Rayleigh number. So RA, not RE. So RE is Reynolds. This time it's RA. That's the Rayleigh number. So we will just have a bunch of equations for different configuration, and each one of them will tell us the Nusselt number is function of the Rayleigh number to power whatever, multiplied by coefficient whatever. And you get the Nusselt number, from it you get the H, and you say Q is HA delta T. Right? That is the deal today. Right? He will try to prove to you why that Rayleigh number is responsible for that movement. Right? And I really would encourage you to try to drive this yourself. When I was undergrad, I used to drive every single equation that would come. I would just go home and drive it, just because I was scared that the professor will actually ask us to prove, and we didn't have open textbook. So our course was closed textbook. So I was worried that they will ask us to prove the equation. So I would really try to develop them all by myself. They never ask us to develop the equation, but I end up learning a lot by doing this. So I would encourage you to actually learn how did this equation come to, because you can prove it in this, in simple cases, you can actually prove why the heat transfer is function of the Rayleigh number. But the main motivator we said was the fact that you get lighter, or basically this, partial rho, partial T. So certain fluids their density will change a lot, all right, when they get, when the temperature gets changed. So if you heat the air, the density will change a lot, all right? So that thing that will calculate 1 over rho partial T at constant pressure, that's called the volume expansion coefficient, beta, right? So for fluid, liquid, you have tables for that. It will tell you what is beta at different temperature, all right? So if you are solving a liquid, we will have to open a table and get it. But for gases, ideal gas, B equal rho RT, you can get partial rho partial T easily, all right? Because we know that P is rho RT. So if you want to get partial rho partial T, we will just have to differentiate rho with respect to T and keep the P constant. So it will turn out that for ideal gas, beta is simply 1 over T. Of course, the most famous mistake that students do in the exam when they try to calculate beta is, right, they put in degree C. No, it should be in Kelvin. Right? So, and it's say over here. So beta is 1 over T. That beta is basically very important for that Rayleigh number calculation. Right? That is the reason why the fluid will go up when he gets hotter. Because his density become really different when he gets hotter, and that create the buoyancy force that make him. So I told you will not see Reynolds number, but actually there is laminar and turbulent. So if we manage to see the flow, this is a hot plate, for example. And so as a result, that hot plate next to an air will make the air go up. The air will get heated and go up. And this is an actual picture. You can actually see the air with a certain experimental technique. You will hear about them when you go to, say, experimental fluid mechanics course. You will see how we can actually see the air moving, but you can. And you can see that at small velocity, the flow will be laminar, but once this thing is very, very long, or the velocity is very, very high, eventually he become turbulent, and you start seeing all this fluctuation. So it's not just the air moving in one layer after the other, but they actually just start to pump. And this equation over here, this is the mother of all equations in fluid mechanics. Okay, this is the Navier-Stokes equation. And of course, it's horrible because partial differential equation, and even more horrible it is. What is even more horrible? It's non-linear. You have u multiplied by partial u partial x. You solve this equation to come up with what? To come up with the velocity profile over here. You would like to know what is the velocity so that you can calculate how much heat energy they are taking out, and then you calculate the energy leaving, the Q that's leaving this plate. So you actually need to solve this equation. We are not going to solve it, but he will show you how to solve it. I don't want you to worry about that solution. Right? So basically, again, you will solve this equation in simpler form, because in all its majesty power right now, you cannot solve it. Right? Because it's partial differential equation and nonlinear. That's really hard to do. Yeah, you can do it computationally. You can do it also for a very simple case. But it has those convection term, and it has this diffusion term, or the viscous term, and it has the pressure term, that's a source term, and it has the gravity term. It basically say, because of your weight, the earth will pull you down. The gravity field will take you down because of the mass. Well, it's this mass that, or this source, that term, that will actually drive natural convection, because the density will change. All right? So he can change that density to temperature by beta. Remember, beta was 1 over T? And so he can change that term to beta. And then the equation, rather than having like a flow in a pipe, what drives the flow? It's the pressure term. It's the pressure gradient that you create in the pipe. The pump at the beginning of the pipe is what pushes the fluid through the pipe. Over here, it's the gravity that's driving the natural convection flow. Or it's basically the temperature difference. The fact that the temperature is really hot at the wall compared to T infinity, that's what will make him go up. All right? So he will try to solve this equation in the next few pages. Right? And here is his boundary condition. So the boundary condition is no slip boundary condition. Okay? And the Ts at the wall and T infinity far away from the wall. So you have Ts at the wall, right? And the fluid next to it, the one that's just sitting into it, will just have to have Ts. But far away, there is basically T infinity, and there is temperature profile between the two of them. And it's the natural convection is what's trying to bring T infinity all the way down to here so that you would improve the heat transfer. All right? He turned the equation dimensionless, and when he does this, when he turned the equation to become dimensionless, rather than u, it's u over a characteristic velocity scale, for example, it will turn out that it's this number show up. This dimensionless number show up in the equation, and this dimensionless number is called the Kirchhoff number. I told you there's something called the Rayleigh number, but the Kirchhoff number is basically the Kirchhoff multiplied by something will end up being the Rayleigh number. All right? So the Kirchhoff number is G beta Ts minus T infinity over kinematic viscosity. All right? And you can see, just like the Reynolds number was rho Vd over mu, or it's basically what's trying to make the flow turbulent and what's trying to keep the flow laminar, the ratio between two forces, one of them trying to push in one way, the other one's trying to resist the motion. Well, over here, here's what's trying to make the flow move. It's the buoyancy, which is G multiplied by, supposed to be G multiplied by density difference, but instead it's G multiplied by beta time temperature. Okay? So, because the temperature multiplied by beta become density difference. Right? So, although you are not required to drive this equation at all, and you will just eventually just use the equation for Nusselt number, but I can give you multiple choice where it would say, for example, you know, those two fluids, which one of them will go faster? And you would basically say, well, the one with the largest beta, you know, the one that will, his density will jump with the smallest temperature change, that's basically could move faster. So you need to understand the physics also, so that when you are using the equation and your eye, when you are copying from the textbook, you forgot the beta. If you really understand the physics, you say, wait a minute, where's my beta? I need to have a beta. Where is my G? How come this guy, it's like if someone understand what is the Reynolds number and he's copying it from, copying the formula from the book, and he forgot the mu and it's rho Vd, he understand the physics. He understand that, well, the Reynolds number is the ratio between two things. I have to have something down. Maybe I don't remember what was down there, but I need to have something down, right, in the denominator. So anyway, so here is my Kirchhoff number, and it's G, and you stick to SI, you will not go wrong. So meter per second square, beta in 1 over Kelvin. Ts minus T infinity, it doesn't matter whether it's degree C or degree Kelvin, because it's delta T, it's difference. So whether it's 300 minus 290 or 25 minus 15, it doesn't make a big difference, any difference. All right? So now, this part is saying that, and actually when you look to this equation too, there is another contribution from, so one source is basically the buoyancy force, but there is also, there could be a Reynolds number, could do something as well. So this is when, and we'll talk about this at the end of the class. There's one part for that. What if the egg is trying to get cooled, but you are also, this is you are also trying to blow into it, okay, with V. So this is natural convection or forced convection or both of them? Well, it depends on how hard you are blowing, right? If you are like my son and you're not going to do anything, he's 4 years old. So I have to always help him, you know, and like basically to make the food a little bit colder. So there is a ratio that we will check, and I bet it will have the Reynolds number and some kind of Kirchhoff number or Rayleigh number that will basically tell us, should we forget about the forced convection, or should we forget about the natural convection, or should we include both of them in the calculation? And when we include both of them in the calculation, what are we going to do? We are going to say that H is H plus H, like total H is H convection plus H, you know, H natural convection plus H forced convection, or what? There is a method to actually include the two of them. All right? But that ratio is Kirchhoff number over Reynolds number square. And if it's smaller than 1, then of course that means the Kirchhoff number is very, very weak, and it's all force convection. Go to the chapter on external force convection. And if this ratio is much bigger than 1, Kirchhoff over nu square is much bigger than 1, that means that forget about that force convection, this problem can be solved in this chapter. And if that ratio is around 1, and around 1 mean that 0.5, 1.3, if it's in that range, then we'll have to deal with 2 of them. We'll solve the problem twice, and we will figure a way to add those 2 h's together. Does this make sense? Huh? Okay. Right, that's what he's trying to say over here. All right. So the formula eventually become Kirchhoff number times Prandtl number. Just like before it was Reynolds multiplied by Prandtl. Remember, every forced equation, forced convection equation, we had the Reynolds multiplied by Prandtl. Because the Reynolds told us how quickly the flow is moving, and the Prandtl did what? The Prandtl was the ratio between, does anyone remember?
How the boundary layers propagated the thermal and
right, the ratio between the momentum boundary layer and the thermal boundary layer. The ratio between nu and alpha. The kinematic viscosity, meter per second square, and meter square per second, and the diffusivity, thermal diffusivity alpha, meter square per second. All right? So the Nusselt number, in this case, will be a constant multiplied by Kirchhoff times Prandtl to power n. So since Kirchhoff and Prandtl next to each other, they combine them together and become the Rayleigh number. So you can see the Rayleigh number is simply the Kirchhoff multiplied by the Prandtl. Right? So all problems basically will start with, let's calculate the Rayleigh number, right? Or the Kirchhoff times the Prandtl, and then go find the right equation for the Nusselt number, pick that equation, calculate the Nusselt, calculate the H, calculate the Q. Okay? And so once you get that, of course, you get the Q is HA delta T. And he's basically telling us that the properties are evaluated at the film temperature. Right? Ts plus T infinity. Ts is the surface temperature, T infinity is the air or the water far away from the wall. Okay? And so here are the table of equation. So vertical wall. Right? Vertical wall sitting at Ts, we got this one and that one. So the Nusselt is 0.59 Reynolds to power 14. Sorry, Rayleigh, I keep saying Reynolds. Rayleigh number to power 1/4 for that range, and for higher range it's 0.1 Rayleigh to power 1/7. And you have equation for a horizontal surface with hot facing up. So that's pretty good for cooling, right? If the hot surface is facing up, the air will get hot and get away, right? But if the hot surface is facing down, what will happen? He's trapped. He will get hot and he will just basically stand here. And the surface will get hotter and hotter because this boundary layer basically will get bigger and bigger. Like more and more stuff will get hotter, and they cannot just basically so in your house, you know, in the summer, you would like to basically send the cold air up so that it falls down on you, right? You don't want to send the cold air at the bottom of the house. You will never basically go up. Your feet will be very cold and you are sweating on top. And same thing in the winter for hot. If you want to warm the house, if you just send all the hot air on the ceiling, okay, it will never really heat the rest of the room. It will just sit there, right? So because of this configuration is annoying for heat transfer. And you can look at the equation for Nusselt number over here, right? And this is not just for hot surface facing downward, but we can also think about cold surface facing downward. That's also annoying, right? No, not cold surface facing upwards. cold surface facing upward would be the same thing. Cold surface facing upward, it's also very annoying for the heat transfer, because the air will just get cold and get stuck. He will not go anywhere. Right? And this hot surface facing upward is the same as, that's pretty good for heat transfer, is the same as cold surface facing downward. The air will get cold and will start dropping. Alright? So that's what it says over here. So we will just, and this is the flow for a vertical cylinder, and he's saying that the vertical cylinder can be treated as vertical plate when the D is greater than 35 L over Kirchhoff number. So basically saying when the diameter is much bigger than the length, you can treat this as vertical plate. So basically what he says that as the diameter get bigger, the curvature lose its effect, and this thing would feel as if it's a flat plate. Just like we on the ground right now, we think the ground is flat. Why? Because the diameter is so big compared to our height. Right? If you are really, really tall, we would see. Right? Or basically if you take an airplane up very, very, very high, like the blackbird, basically. If you take the blackbird, you fly there, you can see the curvature of the earth from the blackbird. But other than that, you will not be able to see it. So anyway, so you have all those relations that basically allow us to calculate the Nusselt number. All right? And actually, let's jump to an example before we go to the rest. So here is a flue gases are released to the atmosphere using a cylindrical stack. Right? So the hot gases are going in, and the temperature of the stack is like 40, and the air is sitting at 10 degrees, and you have the length and you have the diameter. All right? And he said the rate of heat transfer from the stack with and without wind are to be determined. So in this example, he would like to get Q dot natural convection and Q dot with forced convection. He actually solved, when he said there's a wind, he will give you the velocity for the wind. So let's solve the natural convection first. What do we do? Q dot would be HA delta T. And then we have to come up with this H. So we have to tell ourselves, well, we need a Nusselt number. Well, does this cylinder, when we look to this table, I have to go to the table and say, well, here's vertical cylinder, and here's horizontal cylinder, and this is a sphere, and this is a flat plate. So he said that cylinder can be treated as a flat plate if D is greater than 35 L divided by the Kirchhoff. So I have to get the Kirchhoff to make sure this works, that D is really greater than this. The Kirchhoff number was that G beta 1 over T, Ts minus T infinity. I got that. Kinematic viscosity, and the Prandtl, I need a temperature to get those guys. The temperature is the film temperature, Ts plus T infinity over 2. Once I have the film temperature, I can get my V and Prandtl. That L, that's the characteristic length of the problem. And next to each table, he will tell you what's the characteristic length. So for example, a vertical plate, the length that makes sense in the problem from the physics point of view is the height. So that plate, and so this is a big error actually, or a big mistake that students can make. You have a plate like this, say 4 meter by 3 meter, vertical plate, 4 by 3. Which length you should use for calculating the 4? And it's not just, I know it's 4 because this is what this table is telling you, but also you should tell yourself that 3 is not really important. Why? Because the convection happening here is the same as the convection happening here is the same as the convection happening here. This is just a repeat of the same flow. But if this length rather than 4 become 100, it make a difference. The boundary layer thickness become really big. The flow could become turbulent after a while. So it's that length that make the difference. All right? Anyway, for us it's much easier because this is what the table is saying. It's saying the vertical is the length, characteristic length. All right? So for example, on a horizontal surface, that could be confusing. On a horizontal surface like this, Should I use the width or the height or the length? So that horizontal surface is also 4 by 3. Which length I should use? So he basically tell you it's area surface divided by the perimeter. So area over the perimeter. Right? So the area, if this was 4 by 3, the area would be 4 times 3, and the perimeter would be exactly 7 plus 7. Correct. All right. So he calculate the beta from 1 over t, and see all those things are the k and v and the parental, they are all this solution. You have it on the lecture. So all those guys are at the film temperature, and then he made his check to make sure that it works, and therefore he can actually treat it as a flat plate, a vertical flat plate, and he used this equation. So why he used this equation? Because he calculated the Rayleigh number, and the Rayleigh number was 2 to 10 to power 12. So when you go to the table for a flat plate, you have 10 to power 4 to 10 to power 9, and you have 10 to power 10 to 10 to power 13. So we are here, right? We are 10 to power 12. So we have to use this 0.1 Rayleigh to power 1/3. If the Rayleigh number was smaller, we would have used this. Okay? So we end up using this because the Rayleigh number was 2 10 to power 12. All right. So he got the Nusselt number, and therefore he got his H. And from the H, he would say Q dot is HA TS minus T infinity. All right. Now, if this was forced convection, that was the second part of the problem. And he said the wind was 20 kilometers per hour. So that's external convection. So I bet the Nusselt number would be Reynolds and Prandtl. The Nusselt number would be function of Reynolds and Prandtl. So we have to calculate the Reynolds number. We have to basically calculate the Reynolds number and then use this equation for a flow over a cylinder. And from that, you will basically get the Nusselt number, and from it, you will get the H. And then you would say Q is H A delta T. Note that over here, he totally ignored the natural convection when he calculated the forced convection. So later in the course, in the chapter, I will show you that we have to check the Krashoffs over the Reynolds. And based on that ratio, we will determine should we ignore it completely or should we include both of them in the calculation. All right? So this calculation was for constant Ts. We know the temperature. All right? If we actually don't know the temperature, so this was for constant Ts. If we don't know the temperature but we know the Qs, how is that possible? You have a circuit board, okay? That circuit board basically in your computer or something, whether it's horizontal or vertical, it has all those transistors and stuff that basically generate this much watt per meter square. Okay, those watt per meter square need to get out. They have to get out. So what will happen is the Ts. So if this was a vertical wall, where do you think the hottest point would be? Imagine a vertical wall with all those circuit breakers on them, all those transistor and IC and stuff. The top would probably be the hottest, right? The fresh air would come like this, get hotter and move, and the highest temperature would be over here, right? And there will not be a constant Ts. There will be a bunch of Ts. And eventually, the Q dot that need to get out is the Q dot generated. That watt per meter square multiplied by the area is the Q dot that will come. So, in this case, Q is fixed basically, all right? And depending on how cold the air outside, that will determine the TS. Right? So yes, still Q is HA delta T, but in that scenario, Q is fixed and delta T will be determined based on the H. If you may move the air faster, delta T does not have to be that hot. And if you kill the air to move the same Q dot, to make the same Q dot move, this thing will get really, really hot. All right? So the equation for it, if you know QS, is basically this. All right? So HL K is equal to Q dot SL over K TL over 2 minus T infinity, where TL over 2, that's the temperature in the middle of the plate. Because we realize that the plate will be hottest at the top, coolest at the bottom. So in the middle of the plate, that would be the reasonable average that represents the whole plate. Right? We will actually study this in detail in a second here. So this is basically all those cooling fans. So your motherboard is, say, here, and it's generating all this heat, and you would like to cool this surface. So we'll have two cases. One of them is TS equal constant. So we imagine that we actually have constant TS. And the second one would be if QS is constant, which is the more practical thing. So first, let's assume TS is constant. All right? And you would like to basically cool this guy really, really quickly. So that heat sink, okay, sitting on your processor, if you open your computer, you'll actually see that they have on the chip, they basically have those fins sitting on it. And so, should you make them really far away from each other, or should you pack them really close to each other, those fins? If you make them very close to each other, you can pack a lot of them, right? If we make them every 1 millimeter, you'll have a lot of fins. That proves that increase the area. But on the other hand, what's bad about packing them so close together? Right, you are killing what? You are killing the natural convection. You are killing the H, right? The stuff that we had earlier in the course, that was a single fin sitting by itself. Now, since we are studying natural convection, we have to actually study the fact that if we start packing a lot of them together, their H from natural convection will slow down because the air doesn't have the place to actually start moving up. All right? So there must be an optimum spacing. And I think in the exam 1 year, I asked them to find out that optimum spacing to cool the surface. We'll get the optimum in the next page. But for now, let's assume that he didn't go for the optimum spacing. He have a certain spacing. So S is the fin spacing, so that's the distance between each two fins. And in this case, the thickness is assumed to be very small. The fin thickness is very tiny. Okay, so you will see that he will just assume that the thickness is almost zero, basically. All right, so S is the spacing, and L is the height. And for the width, or the length of this doesn't matter really. From the heat transfer point of view, this happens at every cross-section area. The air just come, get heat up, and leave. And it's repeated through the whole length. All right? So the Nusselt number is going to be this, HS over K. And its function, this is the equation that we're going to use for vertical isothermal plates. All right? If TS is constant, then the Nusselt number, HS over K, and from that you can get your H, and then say that the Q is HA delta T, where A is all your area. Okay? We'll see this in a second. The Nusselt number is 576 over Rayleigh and another Rayleigh. All right? So that's really based on the S, and that really is, here it is. So it's the really number, but the length scale is the spacing, right? There is also really based on the, rather than the spacing, it's based on the length or the height of the fin. Okay. So the difference between them is rather than S cube, you have L cube. So anyway, you will use this equation to calculate the Nusselt number, right? And once you get that Nusselt number, you can get the H, and you will say that the Q is H multiplied by delta T, Ts minus T infinity, multiplied by the area. So what is the area? So it's basically this multiplied by this, right? This is the H multiplied by the length. So notice this is the vertical. So the L is always the height. It's the distance that make a difference with the air, right? So if this guy was sitting horizontally like this, this would be the length. It's the height above the ground. That's the L. And S is basically the spacing between those cells that's going to start generating the inertial convection, right? So that's the L, and that's the H in this case. And so the area is H times L. That's the area of one side. Multiply by 2, because you have double faces. Multiply by N, where N is how many of them per unit, the total number, right? So how many of them you have. So here is the N. So the N should be the width divided by how much does each one of them occupy. So usually the one of them would occupy S plus T, right? S is the spacing and T is the thickness. So this is the accurate equation, of course. He approximated to be like this, and you can only do this if T is really tiny compared to S. So you find yourself saying S is 1 inch and T is 0.0 of an inch. Okay, cancel it. But sometimes people make the fins really thick because they are external fins. They could drop on the ground. It's not like sitting inside the laptop safe from everyone else, but it's rather something on the outside. Then they make it really big. And if the T is really big, then we have to stick to this. Okay, what is that again? He would like to find out how many fins he got. So he would divide the whole width, W, over how much does each fin occupy. The fin occupy the thickness plus the spacing. Okay? Does this make sense? We didn't say anything except that Q is HA delta T. The only thing is that the area is a little bit complicated because there are two sides. And of course we neglected all the edges. We even neglected what? What else did we neglect in the area? The in between. The back is where the energy is coming from. So it's like this is convection from one side. So we even neglected this part. Is that justified? Well, if the fin area is really big, maybe it's justified. If you want to be super accurate, of course, maybe you want to include also those guys. Right? Especially if the spacing is really big. So that would be an area that's also convecting. All right? Anyway, so this is the general formula for the Nusselt number. So I bet this would be at certain spacing. It will have the optimum spacing. It will, and the optimum Nusselt number is this, 1.307. So if I ask you to calculate, if I say it's optimally spaced, you don't even have to calculate the really number. You just go ahead and use this Nusselt number. That is the highest Nusselt number, 1.307. And what is the spacing for that optimum Nusselt number? You get it from here. H S optimum over K is 1.3. So if you have your K and your H, you can get S optimum. All right? Okay? And in either case, whether you are going with the maximum Nusselt or just a regular Nusselt from whatever he has, you will just come here and calculate the Q. H area delta T. All right. So this was the case for constant TS. We actually know the TS. chances are, no, you don't know the TS. Chances are you know the Q. You know how much energy those guys are sending per unit area per unit time. Well, basically, you know the Q dot S, watt per meter square. All right. So per unit area. So that's why you don't see an area. Right? This Q is Q per area. So that small q, or the flux, is basically just H, L, T, L minus T infinity, and that's it. There is no area, right? Because it's per unit area. So again, in this scenario, S optimum, to cool them, because again, if we squeeze them, you will basically annoy the convection. You will not be able to actually move. So S optimum is basically 2.12 S to power 4 really star S. So that really star S is this guy. All right. So for normal spacing, if he give you the spacing and he asks for the HL so that you can get TL, so we know the Q, what he would ask for, and we know the area. The question is, how hot will this chip will go to? Will it melt or not? Right? So Q is given per unit area, right? So it really doesn't matter whether he's 100 meters square or 1 meter square, because Q per unit area is this much. And the unknown is TL. Okay? TL would be here. This is the highest point. The highest temperature would be here. Right? And so to get this, you will get it from this HL, and this HL is coming from that Nusselt number. And that Nusselt number is just a function of, again, as any natural convection problem, is function of the Rayleigh number, which is here. Right? And why it's what's with the star? Well, it's because this is constant Q, it's not constant TS. Right? So you would see it's not function of that Nusselt number, that Rayleigh number, is function of TS minus T infinity. Here, we don't have TS. We don't know it. We are actually trying to solve for it. So it's function of QS. Okay? So the procedure is, you calculate the Rayleigh number, you calculate the Nusselt number, and from that you calculate the H, and from the H you calculate the TL. Alright? He could also ask you for T infinity, for example. He could, that equation, he can basically tell you, well, the temperature was this high in the chip, how hot is the air? Fine, you get the T infinity. Of course, this is would be a little bit more tricky than just the straightforward problem. And again, this is the S optimum to get this thing cooled to the best efficiency. All right? This part, this is basically the cell, the internal cell that would happen, say, in a double glass window. Okay? If you have a double glass window, why do we do that? To improve our insulation, right? You would like to see the garden or the backyard, but still you don't want the glass to actually leak all this heat, right? So you make double glass. The window actually have 2 layers of glass, and in between them there is an inert gas, nitrogen or helium or whatever, and you can tell whether this layer is still there or not. So why they put those guys rather than just air?
Okay.
Lower K probably, right? It's not as conductive. So when I bought my house, I went through the windows and checked if the windows are, if they are not clear. If you start seeing some water droplets inside, some humidity, you know that the seal was broken, and the nitrogen or whatever the inert gas they have, the helium or whatever, actually end up leaking, and you have air inside. And so air usually will have H2O with it. And then when you are really cold in the winter, the H2O will end up condensing on one layer. You will see it will not be clean. You will just see, no matter how much you clean it, you will be able to see that it's basically have humidity inside. All right. So we think that when we do this double glass and we have this inert gas between them, we killed the heat transfer, right? But as a matter of fact, actually there could be a small, a small cell that's moving between the hot fluid, the hot surface and the cold surface. So the cold surface will cool the stuff and take them down, while the hot one will basically heat them and take them up, and you basically will have this cell. All right. So we will not go through the calculation for this guy, but I just want you to know that this will result in eventually, as if you improved your K. That cell that start moving, it will be as if you actually increased your K. So rather than having this K of nice small value, it get a boost by the Nusselt number. All right? That's generating because of the convection. So this, they call it the K, ouch. They call it K effective, or basically the actual K multiplied by the Nusselt. All right? Of course, if we can kill the Nusselt and make him 1 without moving the flow, then you will go back again to the pure conduction problem. We'll skip this thing too, the natural and horizontal. Right. And this is the case when he actually have 2 cylinders. So the cell is actually between the 2 cylinders. And just like when we did the conduction, we had Ti and T out, and we have 2 by K. Remember 2 by K over ln? It was ln R2 over R1 over 2 by K. Ln R2 over R1 is the same as ln D over D. Remember this equation was Q dot was Ti minus T out over 2 by K over ln R2 over R1. And this was the conduction of the cylinder. This cylinder filled with a fluid. So now if you have this natural convection working, same trick, he will actually have K equivalent. He will improve the conductivity, right? By basically moving the fluid himself. Not just, the energy is not just moving from one layer to the other, but he's actually moving itself. And that's the way that you can calculate the improved conductivity. All right, so it's function of the Prandtl number, it's function of the Rayleigh number based on the length, and it's function of this F. That geometry factor is basically how the curvature d out and di over the length scale. And here is the length scale. All right? So in those trapped geometry, all the natural convection is do for you is basically improving your conductivity, making it as if it's bigger. And the same thing for the 2 spheres. Right? So again, this would be the improved conductivity for the 2 of them. Right, now the part where, let's mix first the 2 natural convections, see how we can do this, and then we'll talk about mixing convection with radiation. So now if we have natural convection and forced convection, you have a fan, and this plate is also vertical. So if he's vertical and he gets heated, he will just take the stuff and go out. He will basically manage to cool the plate by itself without any fan. So if you have another fan as well, that probably will help the heat transfer. So you get an extra boost from the fan. But if the fan is actually in the opposite direction, imagine if this is a cold plate, so the cold plate will send the air downward, and you put a fan against it. So now the force of convection on a flat plate is opposing the natural convection from that flat plate. So should we do H plus H or H minus H? In this case, probably H minus H, right? They are not helping each other. They could actually make the air stagnant ideally, you know, like if they are really the same power, they will just stop there without going anywhere. And that's the worst for the heat transfer. So, but it's not simply H plus H or H minus H. Here is a formula. So for combined effect, and this is the problem probably I'm going to have for you for your homework. So one time the fan is helping the natural convection, the other time the fan is opposing natural convection. All right? So of course, we actually resort to this if it's not one of those cases. So the first thing you should do in solving this problem, first decide, is it worth it to consider the other guy? The other guy meaning the natural or the forced convection. So first you check on the other guy. So how do you do this? By calculating Kirchhoff over the Reynolds number square. So if that ratio is much, much bigger than 1, then, well, Kirchhoff is dominant. Forget about forced convection. The fan is not doing anything. And if this number is much, much smaller than 1, well, forget about natural convection. Don't even bother and just go for pure forced convection over a cylinder. Okay? And again, this greater than 1 and much, much smaller than 1, we are talking about, you know, not like 1.2, but, you know, 30, right, 100. Not 0.5, but 0.01, 0.001. Big difference in the number that basically say forget about the other guy. Well, what if it's the same magnitude? Then we go to this. All right? And so it's Nusselt, you add it by the Nusselt number. So Nusselt forced plus or minus Nusselt natural to power n, and the whole thing is to power 1 over n. Okay? What is this n? This n could be 3 or 4. 3 for vertical surface and 4 for horizontal surface. The plus or minus is for plus for assisting and minus, of course, for opposing. If the two of them are acting against each other, not helping, you subtract. Of course, you subtract the big guy minus the small guy, right? You don't want to end up with negative Nusselt number. You are weakening the strong guy by the weak guy, right? And so if they are assisting, it's plus. Also, it's plus if it's the configuration is basically transverse flow. So natural convection is going this way while the forced convection is normal to it. In that case, it's plus. Okay? It will not be negative. They will actually help each other. All right? So that's what. So in this problem, you will basically calculate natural convection from a cylinder. You calculate the forced convection from the cylinder, and you add them in this case, and you subtract them in this case. Okay, you again subtract by this formula. Okay, under the power. Does this make sense? Now, mixing convection and radiation, because that is usually what happens on all those ceilings, you know, our roof, solar cell, heat, with solar water heaters. So you have those two guys working with each other. So Q total will be Q convection and Q radiation. So next, actually, class will have a lecture for radiation. So we'll understand how to do this. But for now, let's just say that it's scale with T to power 4. So rather than in convection, it's T minus T. This time it's T to power 4 minus T to power 4. So T sky or T surrounding to power 4 and T surface to power 4. Okay? And it's multiplied by the area and epsilon sigma. All right? So this, we'll talk about this. This will change a little bit for different surfaces. All right? But that sigma is a constant, Stephen-Boltzmann constant, and this epsilon would be the emissivity of that surface, or how good his radiation is, how easy for it to radiate. All right? And we will just add, if this certain watt per meter square, and this is watt per meter square, you add the two of them together, and that will be how much heat is leaving your surface. All right? Sometimes it could be that radiation is coming while convection is leaving. So the air is colder than you, But say you have a source for radiation that's very hot, that's basically heating you.